All right, in this example, we are going to work with another case where we're going to have multiple intervals that we're going to stack up together. So here we have a antelope, and this is an antelope that can jump really high. So they tell us that to go through the steps of this motion, the antelope's going to go into a crouch, then extend its legs. And when it goes from the crouch to extending the legs, there's an acceleration over a certain distance. Then it's going to leave the ground, jump into the air, and we want to know how high it's going to go. Okay, so it's an object that is going to be moving through the air, so we can model it in free fall once it leaves the ground. So there's going to be a free fall component to it. There's going to be another interval where the antelope is accelerating from the ground before it goes into free fall. So I'm going to draw a little just picture of kind of what's going on over here first, and then we'll do our motion diagram just to help me kind of visualize. So here's my little antelope. So initially, we'll say here's our forelegs, and we're crouched on the ground, and then it's going to be, the legs are going to all be extended, and then it's going to leave the ground, right? We can assume those legs are still extended. So we have kind of these 3 points in time, and we're going to have our two intervals. So there's going to be an interval where we go from crouching to legs extended, and then there'll be another interval where legs are extended and leaving the ground. So these are going to make up our two intervals. I want to kind of do this drawing also to show, so remember we're doing a particle model, so an antelope has kind of a complex shape with its legs and body and everything, and I didn't draw the head or anything here. But we have the antelope body, we're going to just model as a particle. So when I think about like the distance that it gives us, and then when we want to know how high does it go, we want to think about the height being from the position where it has legs fully extended, where it's just standing. So this is the point where it's going to leave the ground. And so if we want to know how high it goes, this is the thing that we're trying to find, right? This is going to be our goal here, is that distance from the legs fully extended position to up in the air. They gave us this information. So they told us that the going from crouching to legs extended, this is the 0.7 meters. So I'm going to just use this. I'll refer back to this, but I just want to kind of put into context when we define our variables. We're going to use this to help us kind of indicate where we want our 0 point to be. So as I go from here to here, so there is going to be an acceleration, right? So we're starting at rest here in a crouched position. We're going to accelerate to legs extended and then leave the ground. So if I do my diagram, we're going to start. So we need to show an acceleration. So there's my acceleration. Once we leave the ground, then we're in free fall. So once I'm in free fall, then I'm going to be slowing down, or my antelope is going to be slowing down. So we're going to have a motion diagram that's going to look something like this. So we have an acceleration upward, that's here. So here we're accelerating up. And then once we leave the ground, we're going to have an acceleration downward. We're going to slow down until that maximum height. So down here, this is our start. And I'll just put in here, this is our crouched position. This part here, this is, I'll just say legs extended. And then up here, this will be our max height, right? Okay, so let's call this one down here. We'll say 1, 2, and 3. Our antelope is moving up, so we'll go ahead and define also the y is positive going upward. We do know this constant acceleration, right? So from 2 to 3 is free fall, which is constant acceleration. And then for the start to, so crouch to legs extended position, we're assuming that also is a constant acceleration process. So let's define our variables. I'm going to say Vy1 and y1, our position and velocity. We're going to do a y2, a vy2, and then a y3, a vy3. So we've got our positions and velocities. We're going to have an acceleration here, a time here, an acceleration here, and a time here. So got all of our variables out. Remember, just like we did when we did the horizontal multi-interval problem, these position and velocity in that middle of the two intervals is going to work for both intervals, right? So that y2 and vy2 is the end of the first interval, and then those are the starting values for our second interval there. All right, let's go ahead and just start plugging in everything we know. So we're starting at rest. So I'll go ahead and do that one is 0. I'm not going to set y1 to 0. So coming back to this piece here, I'm going to set my 0 here at the position where we're going to leave the ground. So I'm going to set my y2 actually at 0. And if this is my 0, then that means this starting point, this has to be negative, right? If this is the 0, these are positive numbers. These are going to be negative numbers. So this one here, this needs to be negative 0.70 meters. The y3 at the top, this is the thing we're looking for. So I'll go ahead and just highlight that in there. We also know at the top, if it's our maximum height, which is what we're looking for, we know that that velocity up there is going to be 0. We also know acceleration information, right? So from 2 to 3, we're in free fall. So that means our acceleration is, we know it has magnitude of g, and it needs to be negative g to make it an acceleration. And then we also know acceleration for this part here. So they told us this is 35 meters per second squared. And I think that's everything we know. I don't think we know our t information, and we don't know our v there in the middle. Okay, so we have a good diagram. We've got our intervals. We have our coordinate system identified. We've defined all of the variables, plugged in all the things that we know. We know what we're looking for, which is at maximum height. So now we want to go grab our constant acceleration equations, right? And so I copied and pasted this little piece here. I don't think that's in your notes, but you have your equation sheet. So these are the equations we're working with. Here I have S's as that generic axis. So everywhere there's an S, we're representing that as a Y. So I'm looking for y3, and I'm looking right now just at this interval from 2 to 3, right? So I will come over here. So first equation doesn't have any position. y3 is my final position. So second and third equation both have what we need in there, what we're trying to find. Both of them have accelerations. So we do know acceleration. We don't know time. So actually, I'm going to go ahead and cross that one out also. I don't know time. So we're really looking, we want to use this equation here, this third one. So I'm going to run through and see, do we know everything? I do know my starting position of that interval is our y equals 0. I do know the acceleration. I do not know this. So I don't know the starting velocity of that interval. I do know the final velocity. Okay, so if I want to solve for that y3, I need to find this. I need to find that vy2. So to find vy2, we're going to look at the other interval, right? So when I need a variable and I don't have it, but I have multiple intervals, we're usually going to hop over to the other interval to find that thing that we need to get to. So now I'm going to look at that first interval. I can use these same equations here. Let me clear those out. So now I'm looking for vy2, which is my final v, which is that one or that one. I don't have a final v in this equation. So if I look at the first equation, I do know my initial, I do know my initial velocity. I do know my acceleration, but I don't know time. So not using that equation. I do know initial, I know acceleration, and I know my displacement. Okay, so we're going to use that third equation there. So as I've done previously, I think I've commented on this. I think it's always really helpful to identify your interval. So we're going to work interval 1 to 2. I'm going to use that third equation there. So this is going to be vy2 squared is vy1 squared plus 2ay1 y2 minus y1. All right, then we're going to run through anything that's 0. So that guy is 0. And then our y2 is 0. So my vy2 is equal to square root of 2 ay1 times negative y y1. All right, and then I'm going to square root that whole thing. All right, when we plug into this, and that's not squared anymore. All right, I'm going to back up here just a second. I'm going to back up and just rewrite this line because I had some type of errors in there. So we're going to say Vy2 is equal to the square root of this, equals 2ay1 times negative y1. Okay, now we can throw in our numbers. So Vy2 is equal to square root of 2 times, we've got 35, I think that was, meters per second squared. And then this is negative y1. Our y1 was negative, so negative of negative. So this is 0.70 meters. And we're square rooting all of that. So Vy2 is going to equal 7 meters per second. All right, they didn't ask us to find that, but we know we needed it. So we needed it to plug into here. So this is 7 meters per second. So now I can go back to interval 2 to 3. So I'll just highlight, we're going 2 to 3 now. I'm going to do interval 2 to 3. And we said, I think, which equation were we going to use? We were going to use that last equation here. So I'm going to do, we have Vy3 squared is Vy2 squared plus 2ay2 times y3 minus y2. Okay, so in here are Vy3. So this is where it's nice, right? We have everything defined for us over here. So we don't have to go back and try to figure out what the problem says. I'm just directly looking in my my setup here where I define variables. So this one's 0, so we can get rid of that. My Vy2, so this is 7 meters per second, so we know that. My ay2 is my negative g, and then my y3 is what we're looking for. And my y2 here, we define that already as 0. So that guy is 0. And this is what we're trying to find. So let's rearrange that. So we're going to say y3 is equal to negative Vy2 squared over 2ay2. And if we plug in our numbers here, so negative of the 7 meters per second, we're going to square that. We have 2 and negative g, so negative 9.8 meters per second squared. So those negatives take care of themselves, and we end up with y3 is equal to 2.5 meters. So that's going to be our final answer. And that is, again, kind of going back to this little picture we made, diagramming what's going on there. That's going to be the height that the antelope goes once it leaves the ground, right? That's how high it's going to be jumping once it actually leaves the ground.